Everyone, and welcome to another episode of CUDA Crash Course. My name's Nick, and we're finally going to cap off our last video on sum reduction. So, I've been looking into this for a little bit, and yeah, one of the optimizations that's kind of out there for doing sum reduction involves doing loop unrolling. However, I implemented loop unrolling, and I actually didn't see a speed up. I actually saw a little bit of a slowdown. So I decided to skip over that section of kind of this optimization guide I've been going through. Part of that might be just because of the fact that I'm doing all this locally on a GPU that's also running graphics. So once you start getting to the really fine grain type optimizations, if you have multiple things running at the same time, that contention is going to be a little more apparent in those optimizations. So I decided to go a different route, and I found something rather interesting that we'll go ahead and look at today. And it's something that deals with the synchronization part of the synchronization and coordination part of GPU programming. And we saw this specifically with this sum reduction kernel. So what we had with the sum reduction kernel was we had to, because I made the claim earlier that there were no GPU-wide synchronization mechanisms. And I was absolutely right about that until CUDA 9 and until Pascal GPU architecture. So, I'm going to call my bad on this one. A lot of times, the code that's available for most people to see and what most people have access to, a lot of times it doesn't use a lot of these programming features. A lot of these programming features are, they're kind of abstracted away from the user a lot of times. And, a lot of research code, of course, doesn't use this. A lot of this is in production code that is just going to be owned by some company and they'll never see the light of day as far as the public. So, but I did come across this, and I'd like to talk about it a little bit. So it's this thing called cooperative threads, right? And so basically we can set up different levels of granularities in order to have synchronization on. So we could have it at a thread block level, at a warp level, and even at an entire GPU level. So we can have, or even inter-GPU. It also supports inter-GPU synchronization, so between grids, which is really interesting. And so I'm going to be looking into this more and probably doing another video on it another day. So what does this mean for us? So previously we had this problem where we had, basically one shot of sum reduction, and then if we needed to reduce, say, a bigger problem or something, because we couldn't coordinate all the thread blocks together, we'd have to just, into kernel, start a new kernel. That last kernel does the final kind of trivial, single thread block sum reduction. Well, we can just get rid of that completely now if we have a GPU-wide, if we can do GPU-wide synchronization instead of just thread block-wide synchronization using sync threads. So that's what we're going to look at today. And we're going to look at their implementation of a sum reduction example from here. And so let's go ahead and look at that. So I've got that loaded up right here. So so what do we need extra? So the only thing we need is an extra header called cooperative threads, cooperative groups.h. This is only CUDA 9 plus. So if you're using CUDA 8 or below, this doesn't exist. I'm sorry. And then we'll go ahead and just use namespace cooperative group so we don't have to, do the scope resolution every single time. And so what really happens here is we'll have a couple different device functions. So we'll have this thread sum, we'll have a reduce sum, and then we'll have the actual kernel that gets launched here. So let's see what we're doing from the main. So we're going to do a little more modern kind of flow to the sum reduction. So instead of manually managing memory, we'll go ahead and use CUDA malloc managed. NVIDIA did a very good job at developing their unified memory, and so the cost is fairly small to use unified memory now. You don't pay a huge cost anymore. You pay a little bit at the very beginning when you first access data, but things like prefetching can get rid of that. But I've kind of ignored prefetching here though. But that's trivially, you can just add that in, right? You call CUDA mem copy prefetch async, whatever the function name is. and you can just automatically start prefetching. But that has nothing to do with correctness. So then we can also, so just initialize a vector, and then we'll do the same thing. So we'll just have, you know, a thread block size of 256, and then a grid size. We'll just have, you know, we'll launch as many threads as we have elements. Okay. And then something a little bit different. So we'll go ahead and use dynamic shared memory. So in the past, we've used static shared memory, where we have, you know, a macro up here that just has a shared memory value in it, and then that shared memory value is like used inside of a __ shared instead of like a device function or something. So now if we declare extern shared int temp and then this blank right here, so this allows us to, you know, if we don't necessarily know how much shared memory we need at compile time, if you do it this and pass it as a parameter, you can wait for runtime to actually have that information. But other than that, all we're going to do is pass it the, you know, unified memory pointers that we get from CUDA malloc managed for sum, and then data and in, right? And so here, you know, for sum, actually we only need one, right? Sorry, not one. We just need size of int, right? So for, oops, and one more print. Right, so all sum is the final result. So we don't have, we're not, you know, we're not going to have this huge, big, you know, multiple vectors and all that we're computing the sum into. We're just going to do it in place this time. So let's go ahead and look at where it starts. So it starts, of course, at the global. This is our entry point kernel, right? So like I said, we've got int pointer sum, int pointer input, and then int in. Then we've got some shared memory that we allocate as temp. But actually, before we even allocate the shared memory, up here we've got thread sum, right? So int my sum is equal to thread sum, and we pass it our input, and we pass it the number of elements, right? And so then we call thread sum right here. Now thread sum looks very similar to the other sum reduction kernels we've looked at in the past. Basically what we do is we start out by, so this, we have a boundary right here. So first we figure out what thread it is, you know, totally inside of our big linear array of threads. And then we say, okay, well, I just want the first quarter of the threads, right? So while I is less than n over 4, right? And then what we'll go ahead and end up doing is every single time we'll march over by whatever the block dim is times the grid dim.x, right? And so basically we're going to kind of just block march over this entire array. But we're going to do something a little bit different in this inner loop, which is this int4, right? So there's these things called, you know, we can do these like vector memory operations. So basically what int4 is I believe if you actually look at its implementation, it's just a struct. And it's a struct that has 4 fields in it. It has int x, or it has 4 integers, x, y, z, and w, right? The names x, y, z, and w don't really matter. They're just 4 integers, so a total of 128 bytes. Now, you may ask, why are we doing this? Well, it turns out if you do something like this, it's actually a pretty good optimization once you get down to the low-level assembly of the low-level SAS assembly, the machine ISA that is actually running on the GPU. What it ends up doing is, you know, we're just casting just an array as this int4 struct. And so when we actually do this load right here, right, of whatever, you know, I position, so every I will load, you know, a different 4, right? So it'll march over by 4 because we're casting it, you know, as a struct that has 4 entries. So, you know, after we cast it, you know, entry 1 will actually be 4 ints over, right? Entry 2 will be 4 ints over. So what this does for us, it actually makes the SAS do these 128 byte loads instead of doing 32 byte loads for each individual field. So you can actually reduce your instructions by about a quarter, right? And so the caveat is these have to be consecutive, right? These have to be consecutive addresses right here, which in our case, you know, they are. And all we're doing is we're summing together these things. And so what we'll do is every thread, we'll go ahead and just add these 4 entries together, right? So every thread, we're doing a quarter of the threads that we have total in the system, right? And then each one of those will add together 4 things, but we're doing this big vector load, right? And we can get that by, it's not like a specific thing that we're calling. It's just that, when the compiler sees this, it goes, okay, I know that an int4 has to be 4 consecutive addresses in memory, right? So I'll load them all at the same time. So it's a little, I don't want to say a trick that you can pull on the compiler, but it's a little hint you can give the compiler, right? And then it just returns the sum of this, right? As after this iterates over. Okay, so then what do we do, right? So we've gone over everything. So then we actually get to the shared memory side of things. So then we have, we want to calculate, for each of the blocks that we have, we want to go ahead and calculate, what's the sum for every single one of these blocks. So we're doing a little more generally now, instead of just assuming, 256, or assuming that we have 256 thread blocks that get launched, and then each of those thread blocks has 256 threads. We've kind of gotten rid of that abstraction, right? We've gotten rid of that strict requirement. So then we have this right here. So this is our first part of cooperative groups that we've seen, and so that's this auto g equals this thread. So we're also using some C++11 stuff in here. So this thread block is just a unique identifier that. So this will be a cooperative group. That's what this type will be, and what this will end up being is unique identifier for this thread block. So if we found out which block ID this is within the grid specifically, it's the same thing as doing this cooperative ID, except now we have a nice interface to do that with. So this allows us to do synchronization for a block, but instead of having to calculate anything, we can just do it with G explicitly. And then if we, where this is really nice, or a lot more nice, is if, say, block this reduce sum, right? So we have another thing right here that does the same. So this will reduce down all the data that's mapped to a particular thread block, and it does it in a lot of the same way. So it does it for, the size of a thread block, right? So that's what we're passing in. We're passing in a thread group. In this case, the thread group is a thread block because it's this thread block. And so there'll be 256 threads in it. So this time we're just reducing 256 elements into one element. And we're passing in this temp, which is actually shared memory. So what we'll do is we'll load a value into shared memory based upon a lane. And then we'll go ahead and then just add into these lanes. And because we're doing shared memory, we have to sync, right? So you may just wonder, well, I know what sync threads is. Why don't I just use sync threads? Well, you can use sync threads. That's perfectly legal. But the reason why this is a lot nicer is because, previously, if you just threw sync threads in here, it would work just the same. But, when you called reduce sum here, you have no idea that there's a synchronization requirement in reduce sum, right? And that's dangerous. And so why is that dangerous? So let's say if this was a much more complicated kernel, and we had, control flow divergence here. So not all the threads actually went into reduce sum, right? So then we would just deadlock, right? Because not every thread would hit the sync threads here. But now that we have this, we're using cooperative groups, we know, okay, I'm passing a group of threads in here, and then the group of threads, we can sync on it. So there's some tie between knowing which threads are going where, and then you can do the synchronization like that. So it allows you to follow a flow of synchronization and what groups of threads should be doing at any given time, instead of just having to rationalize it and kind of think it out in your head, or maybe have really, really detailed comments. Okay. So what this will do is, so lane, so we can get the thread rank, right? So that'll just be the thread inside of a thread block. And so what we'll do is we'll go ahead and return the value, right? And the value will just be, this partial sum, right? And so then we'll have a block sum, right? So that's what gets returned there. So then, at this point, we have every single one of our block sums calculated, right? So, good on us. So now we have to put them all together. Now, previously, when we did this, we had to split this by a kernel boundary. But, we really don't need to do that because of, the way we've structured this. So instead, what we can just do is we can just, we can look at, for, our entire, for every single thread block right here, we can figure out if the thread rank is equal to 0. So if it's a 0 thread in there, and we can just do an atomic add. Now, this is the first time we've seen an atomic add, so it requires a little bit of talk about atomicity, right? So what is atomicity? So atomicity just says that you're going to guarantee that there's only one write going on at any given moment. So that means that if, say, two people are writing to the same thing, there will be one ordering of those writes. So you won't see, kind of a combination. So you won't see, let's say, if, we have a variable, it's set equal to 1, and then we have two threads. One of them's trying to add 2 to it, another one's trying to add 1 to it. Well, if we didn't have write atomicity, what could happen is both of them could read 1. So that part is fine. One of them could write 2, right? So let's say 1, and we're adding either 2 or 3, right? From two different threads, just for simplicity. So 1 could write 1 to it, right? So we'd have 1 plus 1 is 2. But this other thread read that value as a 1 as well. So he does 1 plus 2, and he writes 3, right? And so which value is correct? Now, when we were programming this, we probably assumed we would get the result of 1 plus 2 plus 3. And we could still get that, but it's not guaranteed. Now, all this atomic add guarantees is that all of these writes that will occur from all of these threads, they will all be serialized. So all the writes will happen in one serial order, and they'll all be seen. So in this case, we're just collecting from every single thread block. Every thread block will launch an atomic add, and so we'll compute an entire sum this way, right? So we'll basically collect all the thread blocks' partial sums using this atomic add instead. So this isn't specific to cooperative threads. Atomic instructions have existed in CUDA. What is specific to CUDA are things like, this G sync, right? And this thread block and things like G.size or thread rank, right? Okay. So let's go ahead and run this. So we'll go ahead and run this with, we'll do kind of a different size. The performance is not I'm not going to do a performance comparison on this one, mainly because we're using CUDA malloc managed, and I'm still getting the hang of how this works with cooperative groups. So we've got the functionality down, but if we wanted to make this even more optimized, we could, right? Because we could make sure we didn't have any penalty whatsoever by just doing CUDA malloc and CUDA memcopy instead. And we could be a little more careful with our grid size dimensions and do those same optimizations we saw in the previous ones. But this is an alternative way. So there's a lot of ways to implement something, and this is one. And what this saves us is an entire kernel call, right? So we have one kernel call now instead of 2. So we have a lot more readable code, right? So let me get rid of this because that's doesn't actually work anymore. So let's go ahead and compile this, right? So we'll do rebuild. And then we'll run this. This only works if you're doing 2 to the 16, because 2 to the 16 is 65,536. All right. So let's see what we get. Right. So we get 2 to the 13 out, right? So which is 8192. So 2 to the 10 is 1024. 11 is 2048. 12 is 4096. 13 is 8192. So we got the right answer. And you see, we only have to do a single kernel call. And so we were, a lot of this comes down to programmability and, maintainability of code. So that's going to go ahead and do it for this episode. This is, we kind of went over cooperative groups here. Unfortunately, IntelliSense doesn't like the highlighting a lot of the cooperative groups things, so maybe we could fix that sometime. All right. So as always, feel free to check me out on github.com/coffee4arch, where we have all of the videos, or all the code that we use in these videos. So we looked at CUDA programming today. Here's all the CUDA programming previous videos. Here's all the links to the code for all those videos. So like all the previous vector sum reduction stuff. The next thing we're going to be doing is we're going to be doing some sorting algorithms. So we're going to look at 3 steps of optimization for merge sort. So stay tuned for that. But other than that, I'm Nick from Coffee4Arch, and I hope you have a nice day.